A binary search tree, BST, is a type of binary tree in which every node has a key, and all keys in the left subtree of a node are smaller than the node's key, while all keys in the right subtree are larger. This property enables efficient search, insertion, and deletion operations and forms the foundation for many advanced data structures and algorithms. BSTs are widely used in scenarios where dynamic, ordered data storage is required, such as implementing dictionaries, sets, and symbol tables in compilers. Understanding the operations of BSTs is essential for leveraging their full potential. One of the most fundamental operations in a BST is insertion. Inserting a node into a BST involves comparing the new key with the root node and recursively moving either left or right, depending on whether the key is smaller or larger. This process continues until a suitable leaf position is found, where the new node is added. The insertion process ensures that the BST property is maintained. For example, if a BST contains the nodes 50, 30, and 70, and we wish to insert 40, the algorithm would start at the root, 50, move left to 30, then move right because 40 is larger than 30, and finally place 40 as the right child of 30. The time complexity of insertion depends on the height of the tree. In a balanced tree, insertion takes O log n time, while in a skewed tree, it can degrade to O n. Proper insertion ensures the tree remains ordered and ready for efficient search operations. Search is another key operation in BSTs and closely mirrors the insertion process. Searching for a key begins at the root, comparing the target key with the current node. If the key matches, the search is successful. If the key is smaller, the search moves to the left subtree. If larger, it moves to the right. This recursive approach allows BSTs to efficiently find elements in O log n time in balanced trees. For example, in a BST containing 50, 30, 70, 20, 40, 60, and 80, searching for 60 would move from 50 to 70, then to 60, successfully finding the node. The BST structure makes searches far faster than linear searches in unsorted lists. Deletion is the most complex BST operation because it requires maintaining the BST property after removing a node. There are three main cases for deletion. The first case is deleting a leaf node, which is straightforward. The node is simply removed, and its parent pointer is updated to null. The second case involves deleting a node with one child. In this scenario, the node's parent is updated to bypass the deleted node and directly point to its child, maintaining the tree's structure. The third case is deleting a node with two children, which is more intricate. To handle this, the algorithm finds either the in-order predecessor, the largest node in the left subtree, or the in-order successor, the smallest node in the right subtree, copies its value to the node to be deleted, and then recursively deletes the predecessor or successor node. This ensures the BST property is preserved. For example, deleting 50 from a BST with nodes 50, 30, 70, 20, 40, 60, and 80 would involve replacing 50 with its in-order successor, 60, then removing the original 60 node. Traversal operations are essential for accessing and processing all nodes in a BST. The primary traversals are in order, pre-order, post-order, and level order. In-order traversal visits nodes in ascending order by recursively visiting the left subtree, the current node, and then the right subtree. Pre-order traversal visits the current node first, followed by the left and right subtrees, which is useful for creating a copy of the tree or serializing it. Post-order traversal visits the left and right subtrees before the current node, often used for safely deleting all nodes. Level order traversal, implemented using a queue, visits nodes level by level, starting from the root, and is helpful for visualizing tree structure. Traversal operations always take O(n) time, where n is the number of nodes. Since each node must be visited, BSTs also support finding the minimum and maximum values efficiently. The minimum value is found by continuously traversing the left child from the root until a leaf is reached, while the maximum value is found by moving to the right child repeatedly. Both operations take O(h) time, where h is the height of the tree. Other useful operations include finding the successor or predecessor of a node, which are critical in deletion and certain search algorithms. The successor of a node is the node with the smallest key greater than the current node, typically the leftmost node in the right subtree, whereas the predecessor is the largest node smaller than the current node, usually the rightmost node in the left subtree. Balancing is another consideration in BST operations. While insertion, deletion, and search can be efficient in balanced BSTs, unbalanced trees may degrade performance to O(n) for all key operations. To address this, self-balancing BSTs like AVL trees and red-black trees use rotations and color rules during insertions and deletions to maintain logarithmic height. These rotations ensure that no subtree becomes disproportionately taller than its sibling, keeping all operations efficient even in worst-case scenarios. BSTs also allow range queries, such as retrieving all keys within a specific range. This can be done using modified in-order traversal. The algorithm only explores subtrees that may contain keys within the given range, skipping irrelevant branches. This property makes BSTs particularly suitable for database indexing and ordered data processing. Additionally, BSTs can implement dynamic sets, priority queues, and associative arrays, leveraging their ordered structure for efficient insertion, deletion, and lookup. In conclusion, BST operations, insertion, deletion, search, traversal, and auxiliary operations like minimum, maximum, and successor, predecessor finding, form a versatile toolkit for managing hierarchical, ordered data efficiently. Proper handling of these operations ensures the tree remains ordered, supports fast lookups, and can adapt to dynamic changes. By understanding the underlying mechanisms of each operation, one can harness BSTs for a wide range of applications, from database management to compiler design, while also appreciating the importance of balancing for maintaining optimal performance.